I thought I would think about changing your perspective on the world a bit and showing you some of the designs that we have in nature. And so I have my first slide to talk about the dawning of the universe and what I call the cosmic scene investigation, that is looking at the relics of creation and inferring what happened at the beginning and then following it up and trying to understand it. And so one of the questions that I asked you is, when you look around, what do you see? Well, you see this space that's created by designers and by the work of people, but what you actually see is a lot of material that was already here being reshaped in a certain form. And so the question is, how did that material get here? How did it get into the form it had before it got reshaped, and so forth? It's a question of what's the continuity. So one of the things I look at is, how did the universe begin and shape? What was the whole process in the creation and the evolution of the universe to getting to the point that we have these kind of materials? So that's sort of part, and let me move on then, show you the Hubble Ultra Deep Field. If you look in this picture, what you will see is a lot of dark with some light objects in it. And everything but 4 of these light objects are stars, and you can see them, they're little pluses. This is a star, this is a star, everything else is a galaxy. Okay, so there's a couple of thousand galaxies you can see easily with your eye in here. And when I look out at particularly this galaxy, which looks a lot like ours, I wonder if there's an art design college conference going on, and intelligent beings there are thinking about, what designs I might do. And there might be a few cosmologists trying to understand where the universe itself came from. And there might even be some on that galaxy looking at ours, trying to figure out what's going on over here. But there's a lot of other galaxies, and some are nearby, and they're kind of the color of the sun, and some are further away, and they're a little bluer and so forth. But one of the questions that should be to you, how come there's so many galaxies? Because this represents a very teeny fraction of the sky. This is only 1,000 galaxies. We think there's on the order visible to the Hubble Space Telescope, if you had the time to scan it around, about 100 billion galaxies. Right? It's a very large number of galaxies, and that's roughly how many stars there are in our own galaxy. But when you look at some of these regions like this, you'll see more galaxies than stars, which is kind of a conundrum. So the question should come to your mind is, what kind of design, what kind of creative process and what kind of design produced the world like that? And then I'm going to tell you it's actually a lot more complicated. We're going to try and follow it up. We have a tool that actually helps us out in this study, and that's the fact that the universe is so incredibly big that it's a time machine in a certain sense. We draw this set of nested spheres cut away, so you can see it, put the Earth at the center of the nested spheres, just because that's where we're making observations. And the moon is only 2 seconds away, so if you take a picture of the moon using ordinary light, this is the moon 2 seconds ago, and who cares? 2 seconds is like the present. The sun, it's 8 minutes ago. That's not such a big deal, right? Unless a solar flare is coming, you want to get out of the way. You'd like to have the advance warning. But you get out to Jupiter and it's 40 minutes away. It's a problem. You hear about Mars. It's a problem communicating to Mars because it takes light long enough to go there. But if you look out to the nearest set of stars, so the nearest 40 or 50 stars, it's about 10 years. So if you take a picture of what's going on, it's 10 years ago. But you go and look to the center of the galaxy, it's thousands of years ago. You look at Andromeda, which is the nearest big galaxy, and it's 2 million years ago. If you took a picture of the Earth 2 million years ago, there'd be no evidence of humans at all, because we don't think there were humans yet. I mean, it just gives you the scale. And with the Hubble Space Telescope, we're looking out hundreds of millions of years to a billion years. But if we were capable to come up with an idea how to look even further, to sense things even further, and that was what I did a lot of my work, was to develop the techniques and tools. We could look out back to even earlier epochs before there were stars and before there were galaxies, back to when the universe was hot and dense and very different. And so that's the sort of sequence, and so I have a more artistic impression of this. There's the galaxy in the middle, which is the Milky Way, and around it are the Hubble, nearby kind of galaxies, and there's a sphere that marks the different times, and behind that are some more modern galaxies. You see the whole big picture. The beginning of time is funny, it's on the outside, right? And then there's a part of the universe we can't see because it's so dense and so hot, light can't escape. It's like you can't see the center of the sun. You have to use other techniques to know what's going on inside of the sun. But you can see the edge of the sun, and the universe gets that way, and you can see that. And then you see this sort of model area around the outside, and that is the radiation coming from the Big Bang, which is actually incredibly uniform. The universe is almost a perfect sphere, but there are these very tiny variations, which we show here in great exaggeration. And from them, in the time sequence, we're going to have to go from these tiny variations to these irregular galaxies and first stars to these more advanced galaxies, and eventually the solar systems and so forth. So it's a big design job, but we'll see about how things are going on. So the way these measurements were done, it's been a set of satellites, and this is where you get to see. So there was the COBE satellite, which was launched in 1989, and we discovered these variations. And then in 2000, the MAP satellite was launched, the WMAP, and it made somewhat better pictures. And later this year, this is the cool stealth version, the one that actually has some beautiful design features to it. And you see the blown up. The Planck satellite will be launched, and it will make very high resolution maps. And that will be the sequence of understanding the very beginning of the universe. And what we saw was we found these variations, and then they told us the secrets both about the structure of space-time and about the contents of the universe and about how the universe started in its original motions. So we have this picture, which is quite a spectacular picture, and I'll come back to it at the beginning, where we're going to have some mysterious process that kicks the universe off at the beginning, and we go through a period of accelerating expansion, and the universe expands and cools until it gets to the point where it becomes transparent. Then the dark ages, and then the first stars turn on, and they evolve into galaxies, and the later they get to the more expansive galaxies. And somewhere around this period is when our solar system started forming, and it's maturing up to the present time. And there's some spectacular things, and this wastebasket part, that's to represent what the structure of space-time itself is doing during this period. And so this is a pretty weird model, right? What kind of evidence do we have for that? So let me show you some of nature's patterns that are a result of this. I always think of space-time as being the real substance of space, and the galaxies and the stars just it's like the foam on the ocean. It's a marker of where the interesting waves are and whatever went on. So here is the Sloan Digital Sky Survey showing the location of 1 million galaxies. So there's a dot on here for every galaxy. They go out and point a telescope at the sky, take a picture, identify what are stars and throw them away, look at the galaxies, estimate how far away they are, and plot them up, and just put radially they're going out that way. And you see these structures, this thing we call the Great Wall, but there are voids and all this kind of stuff, and they kind of fade out because the telescope isn't sensitive enough to do it. Now I'm going to show you this in 3D. What happens is you take pictures. As the Earth rotates, you get a fan across the sky. There's some places you can't look because of our own galaxy, or because there are no telescopes available to do it. So the next picture shows you the three-dimensional version of this rotating around. You see the fan-like scans made across the sky. Remember, every spot on here is a galaxy, and you see the galaxies, sort of in our neighborhood, and you sort of see the structure, and you see this thing we call the Great Wall, and you see the complicated structure, and you see these voids. There are places where there are no galaxies, and there are places where there are thousands of galaxies clumped together. Right? So there's an interesting pattern, but we don't have enough data here to actually see the pattern. We only have 1 million galaxies, right? So we're keeping like 1 million balls in the air, but what's going on? There's another survey which is very similar to this called the 2-degree field of view galaxy redshift survey. Now we're going to fly through it at warp 1 million. And every time there's a galaxy at its location, there's a galaxy, and if we know anything about the galaxy, which you do because there's a redshift measurement and everything, you put in the type of galaxy and the color. So this is the real representation. And when you're in the middle of the galaxies, it's hard to see the pattern. It's like being in the middle of life. It's hard to see the pattern. In the middle of the audience, it's hard to see the pattern of this stuff. So we're going to go out and swing around and look back at this. And you'll see first the structure of the survey, and then you'll start seeing the structure of the galaxies that we see out there. So again, you can see the extension of this great wall of galaxies showing up here. But you can see the voids, you can see the complicated structure, and you say, well, how did this happen, right? Suppose you're the cosmic designer. How are you going to put galaxies out there in a pattern like that? It's not just throwing them out at random. There's a more complicated process going on here. How are you going to end up doing that? And so now we're in for some serious play. That is, we have to seriously play God, not just change people's lives, but make the universe, right? So if that's your responsibility, how are you going to do that? What's the kind of technique? What's the kind of thing you're going to do? So I'm going to show you the results of a very large-scale simulation of what we think the universe might be like, using essentially some of the play principles and some of the design principles that humans have labored so hard to pick up, but apparently nature knew how to do at the beginning. And that is, you start out with very simple ingredients and some simple rules, and but you have to have enough ingredients to make it complicated, and then you put in some randomness, some fluctuations and some randomness, and realize a whole bunch of different representations. So what I'm going to do is show you the distribution of matter as a function of scales. We're going to zoom in, but this is a plot of what it is. And we had to add one more thing to make the universe come out, right? It was called dark matter. That is matter that doesn't interact with light the typical way that ordinary matter does, the way the light shining on me or on the stage. It's transparent to light, but in order for you to see it, we're going to make it white. Okay, so the stuff that's in this picture that's white, that is the dark matter. It should be called invisible matter, but the dark matter made visible. And then the stuff that is in the yellow color, that is the ordinary kind of matter that's turned into stars and galaxies. So I'll show you the next movie. So this, we're going to zoom in. You'll notice this pattern, and pay attention to this pattern. We're going to zoom in and zoom in. And you'll see there are all these filaments and structures and voids. And when a number of filaments come together into a knot, that makes a supercluster of galaxies. This one we're zooming in on is somewhere between 100,000 and 1 million galaxies in a small region. So we live in the boonies. We don't live in the center of the solar system. We don't live in the center of the galaxy. And our galaxy is not in the center of a big cluster. So we're zooming in. This is a region which probably has more than 100,000, on the order of 1 million galaxies in that region. We're going to keep zooming in. Okay, and so I forgot to tell you the scale. A parsec is 3.26 light years, so a gigaparsec is 3 billion light years. That's the scale. So it takes light 3 billion years to travel over that distance. Now we're into a distance, so that between here and here is the distance between us and Andromeda, right? These little specks that you're seeing in here, they're galaxies. Now we're going to zoom back out. And you can see this structure that when we get very far out looks very regular, but it's made up of a lot of irregular variations. So there's simple building blocks. There's a very simple fluid to begin with. It's got dark matter. It's got ordinary matter. It's got photons, and it's got neutrinos, which don't play much role in the later part of the universe. And it's just a simple fluid, and it over time develops into this complicated structure. And so, you know, now, when you first saw this picture, didn't mean quite so much to you. Here, you're looking across 1% of the volume of the visible universe, and you're seeing billions of galaxies, right, and nodes. But you realize they're not even the main structure. There's a framework, which is the dark matter, or the invisible matter that's out there, that's actually holding it all together. So let's fly through it, and you can see how much harder it is when you're in the middle of something to figure this out. So here's that same end result. You see a filament, you see the white is the invisible matter, and the yellow is the stars or the galaxies showing up. And we're going to fly around, and we'll fly around, and you'll see occasionally a couple filaments intersect, and you get a large cluster of galaxies. And then we'll fly into where the very large cluster is, and you can see what it looks like. And so from inside, it doesn't look very complicated, right? It's only when you look at it on a really large scale and explore it and so forth, you realize it's a very intricate, complicated kind of a design, right? And it's grown up in some kind of way. So the question is, how hard would it be to assemble this, right? How big a contractor team would you need to put this universe together, right? That's an issue, right? And so here we are. You see how several filaments are coming together, and therefore making this supercluster of galaxies. And you have to understand, this is not how it would actually look if you were, first you can't travel as fast, but everything would be distorted, but this is using simple rendering, graphic arts kind of stuff. This is how, if you took billions of years to go around, it might look to you, right? If you could see invisible matter too. And so the idea is, you know, how would you put together the universe in a very simple way? We're going to start and realize that the entire visible universe, everything we can see in every direction with the Hubble Space Telescope, plus our other instruments, was once in a region that was smaller than an atom. It started with tiny quantum mechanical fluctuations, but expanding at a tremendous rate. and those fluctuations were stretched to astronomical sizes, and those fluctuations eventually are the things we see in the cosmic microwave background, and then we need some way to turn those fluctuations into galaxies and clusters of galaxies and to make these kind of structures go on. So I'm going to show you a smaller simulation. This simulation was run on 1,000 processors for a month in order to make just this simple visual one. So I'm going to show you one that can be run on a desktop in 2 days in the next picture. So you start out with teeny fluctuations when the universe was, at this point now, 4 times smaller and so forth. And you start seeing these networks, this cosmic web of structure forming. And this is a simple one because it doesn't have the ordinary matter in it, it just has the dark matter in it. And you see how the dark matter lumps up and the ordinary matter just trails along behind. Right? So there it is. At the beginning it's very uniform. The fluctuations are apart in 100,000 to a few peaks that are apart in 10,000. And then over billions of years, gravity just pulls in. There's a slight over density, pulls the material around in, that pulls in more material and it pulls in more material. But the distances on the universe are so large and the time scales are so large that it takes a long time for this to form. And it keeps forming until the universe is roughly about half the size it is now, and in terms of its expansion. And at that point, the universe mysteriously starts accelerating its expansion and cuts off the formation of larger scale structure. So we're just seeing as large a scale structure as we can see, and then the only things that have started forming already are going to form. Then from then on, it's going to go on. So we're able to do this simulation, but this is 2 days on a desktop. We need 30 days on 1,000 processors to do this kind of simulation that I showed you before. So we have an idea of how to play seriously at creating the universe by starting with essentially less than an eye drop full of material, right? And we create everything we can see in any direction, right? From almost nothing, that is something extremely tiny, extremely small, and it is almost perfect, except it has these tiny fluctuations at a part in 100,000 level, which turn out to produce the interesting patterns and designs we see, that is galaxies and stars and so forth. So we have a model and we can calculate it and we can use it to make designs of what we think the universe really looks like. And that design is sort of way beyond what our original imagination ever was. So this is what we started with 15 years ago with the Cosmic Background Explorer. We made the map in the upper right, which basically showed us that there were large-scale fluctuations, and actually fluctuations on several scales. You can kind of see that. Since then, we've had WMAP, which just gives us higher angular resolution. We see the same large-scale structure, but we see additional small-scale structure. And on the bottom right is, if the satellite had flipped upside down and mapped the Earth, what kind of a map we've gotten the Earth, you could have seen, well, you can kind of pick out all the major continents, but that's about it. But what we're hoping, when we get to Planck, we'll have resolution about equivalent to the resolution you see of the Earth there, where you can really see the complicated pattern that exists on the Earth, and you can also tell, because of the sharp edges and the way things fit together, there's some nonlinear processes. There's geology has these effects in which is moving the plates around and so forth. You can see that just from the map alone. We want to get to the point in our maps of the early universe we can see whether there are any nonlinear effects that are starting to move, to modify, and or give us a hint about how space-time itself was actually created at the beginning moments. And so that's where we are today, and that's what I wanted to give you a flavor of, give you a different view about what the design and what everything else looks like. So, thank you.